struggling with a so-called Hubble tension. But now the James Webb Telescope has detected a very special supernova that appears 3 times in a single image due to the gravitational lensing effect, and thus allows the value of the Hubble constant to be determined to an unprecedented extent. But confusingly, this revolutionary method of measurement sometimes raises even more questions than it answers, and we may have to admit that we are still a long way from understanding the true nature of the universe. To err is human, and Albert Einstein was only human too. In fact, the creator of the theory of relativity was so convinced of the idea of a static, unchanging universe in the beginning that he even added a cosmological constant to his equations. But when Edwin Hubble discovered the expansion of the cosmos based on the escape of galaxies, and Alexander Friedman and Georges Lemaitre also found cosmological expanding solutions to the field equations, Einstein was forced to discard the idea of his constant. Subsequently, the world-famous physicist is said to have even referred to it as the greatest folly of his life. Today, the knowledge that the universe has been expanding incessantly since its inception is part of the basics of astronomy. However, the universe is not expanding into an existing space. Rather, it is space itself that is constantly growing. In principle, the expansion of the cosmos is deduced from objects in space that are far apart from each other. After all, the distance between them is constantly growing. However, when it comes to the question of the so-called Hubble constant, which indicates the speed at which the universe is currently expanding, scientists have 2 completely different methods at their disposal. The first is based on the standard model of cosmology and combines our theoretical considerations with the measurements of the cosmic background radiation. This is another radiation relic in the microwave range, which was created about 380,000 years after the Big Bang and still fills the entire universe today. In any case, this method of determining the Hubble constant gives us a value of around 67. Incidentally, the unit of the Hubble constant is somewhat unusual. It's given in kilometers per second per megaparsec. 1 megaparsec corresponds to about 3.26 million light-years, while 1 light-year is 9.46 trillion kilometers. Conversely, this means nothing more than that the speed at which the galaxies in space move away from each other increases by 67 kilometers per second every 3.26 million light-years. That's an impressive 244,000 kilometers per hour per megaparsec. But it can be significantly faster. As already mentioned, this is only one of 2 methods of determination. The other is based on the observation of objects such as Type 1a supernovae, which always reach the same brightness, or so-called Cepheid stars, whose brightness fluctuates regularly. Against this background, however, the Hubble constant is no longer 67, but suddenly over 73 kilometers per second per megaparsec. Consequently, real-life observations in space also show that the cosmos is expanding 20,000 kilometers per hour per megaparsec faster today than it should according to the cosmological standard model. But how is that possible? How the cosmos trolls cosmology? Well, that is precisely the question. The simplest answer would probably be that the measurements of the past were simply wrong. To test whether we can really trust the data collected by the Hubble Space Telescope, Adam Rees conducted a new series of observations last year using the much more powerful James Webb Telescope. If anyone knows how to get to the bottom of the accelerated expansion of the universe, it's Adam Rees. After all, the American astrophysicist was awarded the Nobel Prize in Physics in 2011 for precisely this work. After Webb had examined over 320 Cepheids, many of which had previously been measured by Hubble, the confusion among experts was even greater. The values determined for the brightness and distance of the Cepheids actually matched those of earlier observations. Accordingly, the new data also yielded a Hubble constant that significantly exceeded that obtained from the theoretical models. Now, however, it's obvious that one has a problem, to put it mildly, when a constant is not constant, not to mention the fact that this constant is supposed to describe the whole universe. At this point, it would perhaps be tempting to claim that the cosmos has trolled cosmology, and Adam Rees also openly admits that our understanding of the universe is possibly anything but complete. It could simply be that we have overlooked something fundamental in our cosmological models. Perhaps there are new types of particles or fields out there that are just as unknown to us as the possibly exotic forms of dark energy and dark matter. This new supernova tells us more about the Hubble tension. Old mystery, new approach. In fact, researchers have now developed yet another method to get to the bottom of the mysterious Hubble tension. However, this novel approach began with a rather simple yet profound question. What are these 3 points of light that weren't there before? In detail, the experts had identified 3 luminous structures in the Webb images of the galaxy cluster PLCK G165.7 plus 67.0 that were not yet visible in the 2015 Hubble images, and which would eventually turn out to be something very special. That was a single supernova that appeared to be 3 supernovae due to the gravitational lensing effect. A brief explanation. In astronomy, the gravitational lensing effect describes the deflection of light by large masses. In this context, the light from a distant source, in this case, a supernova, is influenced by the gravity of another object that lies in front of it for the observer. The basic principle here is that light rays deflected by such a gravitational lens are deflected more strongly toward the mass the closer they pass by it. In simple terms, the gravity of a massive object acts like a giant magnifying glass in space, distorting the light of the structures behind it. How did the international research team conclude that a triple-line supernova is lurking in the Webb images? Brenna Fry from the University of Arizona explains that the corresponding field, called G165, is known for its high rate of star formation, over 300 solar masses per year, and this fact correlates with higher supernova rates. The following analyses confirmed the first suspicion and showed that Webb had indeed captured an explosive stellar death on film. More precisely, we see the violent end of a white dwarf, and thus a Type 1a supernova. In this type, a white dwarf steals matter from its partner star before it reaches the critical mass and explodes. Since these luminous spectacles all have approximately the same initial brightness and also dim to the same extent over time, they are considered popular standard candles among experts. We've already mentioned how important such standard candles are for determining the Hubble constant. This time, the gravitational lensing effect provided researchers with completely new insights. The lens in question is a cluster of galaxies in the foreground that mirrored the middle image relative to the other 2 images. Basically, the light traveled along 3 different paths. Since each path was different in length, but light always moves at the same speed, the stellar explosion was captured at 3 different points in time. To better illustrate this, Fry compares this characteristic to a triple vanity mirror, where we see 3 different images of the same person. In keeping with this, the time-lapse Webb recordings show a mirror on the right in which someone picks up a comb, a mirror on the left in which hair is combed, and a mirror in the middle in which the person puts the comb back down. Back at the research facilities, scientists realized that such a triple supernova, with its time delays, distance, and gravitational lensing properties, holds enormous potential for knowledge of the Hubble tension. Since experts hope to understand the mysterious expansion rate of the cosmos more precisely than ever with the help of this supernova, they promptly named it SN Hope. With a redshift of Z equals 1.78, Hope is one of the most distant Type 1a supernovae discovered so far. In fact, the stellar explosion occurred around 10.3 billion years ago. 7 subgroups of the HL research program analyzed Hope in terms of its information on the Hubble tension without exchanging their results. The idea was that the corresponding values should be determined independently of each other and without bias. When the time came for the teams to present their gravitational lensing models, the value of the Hubble constant was neither 67 nor 73, but 75.4 kilometers per second per megaparsec. What does this mean? On one hand, the result is consistent with other measurements in the local universe. On the other hand, it's once again in contradiction to the values determined for the younger universe. It should be noted that this was only the second measurement of the Hubble constant using this method, and the first to use a standard candle. Nevertheless, the value obtained this time also differs significantly from the theoretically derived value, and we simply do not have a clear explanation for this. Astronomers now hope to further improve the accuracy of their measurements through additional observations with the James Webb Telescope. If Webb's keen, I can spot other standard candles in the future. The day may come when the mystery of the Hubble tension finally belongs to the past. And the times when you haven't clicked subscribe yet could finally also be a thing of the past. Feel free to hit the like and subscribe buttons so you never miss a new video from our Digital Discoveries channel. We'll see you soon.